Welcome to this video, where we will explore one of the most famous and mind-bending thought experiments in quantum physics, Schrödinger's cat. This thought experiment was proposed by the physicist Erwin Schrödinger in 1935 to illustrate the strange and counterintuitive principles of quantum mechanics, especially the concept of superposition. Today, we'll explain Schrödinger's cat in simple terms, explore what it tells us about the quantum world, and discuss why it continues to fascinate scientists and the public alike. Imagine a cat placed inside a sealed box. Inside the box, there is also a tiny amount of radioactive material, a Geiger counter, and a vial of poison. The setup is rigged so that if the Geiger counter detects radiation from the decaying atom, it triggers the release of the poison, which would kill the cat. If no radiation is detected, the cat remains alive. According to classical physics, the cat is either alive or dead, depending on whether the atom decays. But in the quantum world, things are very different. The radioactive atom exists in a superposition of states. It has both decayed and not decayed at the same time. Because the cat's fate is directly linked to the state of the atom, the cat itself becomes entangled with the atom and exists in a superposition of being both alive and dead at the same time. This is, of course, not something we would ever observe in reality. We do not see cats that are simultaneously alive and dead. The point of Schrödinger's thought experiment is to highlight a paradox in quantum mechanics. At the microscopic level, particles can exist in multiple states at once, but when we try to apply these principles to the macroscopic world, the results seem absurd. The cat thought experiment illustrates the problem of measurement in quantum mechanics. A quantum system remains in superposition until it is observed. When we open the box to check on the cat, the act of observation forces the superposition to collapse into a definite state. The cat is either alive or dead. This is known as the collapse of the wave function, a concept that has puzzled physicists and philosophers for decades. Schrödinger's cat also demonstrates the difference between quantum and classical reality. In classical physics, objects have definite properties regardless of observation. In quantum physics, particles do not have definite properties until they are measured. The cat's superposition is a dramatic way of showing how quantum rules differ from our everyday intuition. This thought experiment has inspired many interpretations of quantum mechanics. The Copenhagen interpretation, one of the most widely taught, suggests that the act of measurement collapses the superposition into a definite state. Other interpretations, like the many worlds theory, propose that both outcomes actually occur, but in separate, parallel universes. In this view, when we open the box, we experience one outcome, while another version of reality experiences the other. While Schrödinger's cat is a thought experiment, it is grounded in real quantum phenomena. Experiments with particles, photons, and even small molecules have demonstrated superposition and entanglement. Researchers can create systems in which a particle exists in multiple states simultaneously and study how measurement affects those states. These experiments show that the strange principles illustrated by Schrödinger's cat are not just abstract ideas, they are real features of the quantum world. Schrödinger's cat also has practical implications for quantum technology. Understanding superposition, entanglement, and the measurement problem is essential for building quantum computers, which rely on qubits that exist in superposition and become entangled with one another. Managing decoherence and controlling the collapse of quantum states are among the key challenges in creating reliable quantum devices. In summary, Schrödinger's cat is a thought experiment designed to illustrate the counterintuitive nature of quantum mechanics. It shows how quantum superposition allows particles to exist in multiple states at once and highlights the crucial role of observation in determining outcomes. While the idea of a cat being both alive and dead is purely hypothetical, It helps us grasp the strange and fascinating rules that govern the quantum world. By exploring Schrödinger's cat, we gain a window into the mysteries of quantum physics, where reality is probabilistic, observation shapes outcomes, and the universe behaves in ways that challenge our everyday intuition. It is a reminder that the quantum world operates on principles far removed from classical expectations, and that our understanding of reality continues to evolve. Thank you for joining this exploration of Schrödinger's cat. As we continue to probe the quantum world, thought experiments like this one guide us in thinking differently about reality, measurement, and the fundamental nature of the universe.